So we want to take the derivative of sine cubed of x. Well, the way we can view sine cubed of x is simply sine of x raised to the third power. It's exactly the same thing. So this is equal to sine of x all raised to the third power. And essentially what we can do in order to take this derivative is we can use that subconscious chain rule trick that I had just showed you 2 examples ago, where you drag the power down, multiply by the derivative, everything is done. So let's go ahead and do that. If we wanted to drag the power down right over here, this would leave us with 3 times sine of x to the second power multiplied by the derivative of sine of x, which is cosine of x. You want to clean this up a bit. This will be 3 sine squared of x cosine of x. Done. That is our derivative. And if you don't trust the power rule extension, go ahead and do it the long way, where it is that we'll split it up into f of x, g of x, f prime, and g prime, and then we plug everything in its place. Essentially, our outer function will be x to the third, because we will have sine of x trapped within an x to the third function. So our f is x to the third, our g of x is sine of x, our f prime of x is 3x squared, and our g prime is the derivative of sine, which is cosine of x. So we plug in sine of x wherever it is that we see x in our f prime. This will be 3 sine of x squared, so sine squared of x, multiplied by cosine of x. Now do these not match perfectly? That is the derivative of our function, using the chain rule. Now we're going to get into the more than one use of the chain rule in order to evaluate the derivatives. We want to take the derivative of sine of x. So let's take a moment to go ahead and ignore this final outer function. Essentially, what it is that we have here is we have a function trapped within a function within a function. So what we want to do is, because we have 3 functions, we will be using the chain rule twice. Because we have sine of x, which is trapped within sine of x. So before it is that we can evaluate the derivative of sine of x, we need to evaluate the derivative of sine of x first. So what we will do is just that. If we wanted to evaluate this derivative, our outer function and our inner function are pretty clearly defined. It's just a sine trapped within a sine. So our f of x is sine of x, our g of x is also sine of x, and then their derivatives are both cosine of x. So f prime composed of g, we plug in sine of x wherever it is that we see x in our f prime. So let's go and write this off to the side over here. This will be cosine of sine of x multiplied by the derivative of our g, which is cosine of x. And that is the derivative of sine of x. So now what we want to do is take the derivative of sine of x. We've taken the derivative of the inner part of the function. Now let's go and take the derivative of the entire function put together. So here we have a sine of x containing a sine of x. So our outer function will be sine of x. And our inner function will be sine of x. Now this is where chain rule gets a little bit tricky. Now we already wrote out the derivative of sine of x. We have it right over here. The derivative of sine of x will be cosine of x once again. And the derivative of sine of x is exactly what it is that we have here from our previous use of the chain rule. So it's cosine of sine of x multiplied by cosine of x. So, same procedure as before. We take f prime and we substitute in g wherever it is that we see x. So we have cosine of x. However, wherever it is that we see x, we substitute in sine of x. So we've got cosine of sine of x multiplied by our g prime, which is this right over here. Cosine of sine of x times cosine of x. Now you may feel tempted to go and start joining sines and cosines. However, because they're trapped within each other as composition functions, we cannot go and simplify this so that, all right, I see one cosine here, one cosine here. This is going to be cosine cubed of x. One sine here, one sine here. This is going to be sine cubed of x. It doesn't work that way. It's only when they're being multiplied by each other, not when they're trapped within one another. So this is as fully simplified as it's going to get. That is our final answer for the derivative of sine of x using the chain rule. The function we want to take the derivative of is e to the, was it ln or sine? E to the sine of ln of x. E to the sine of ln of x. So once again we have two functions, or rather three functions. So we have an e to the x, a sine of x, and an ln of x. So essentially what we want to start with is the sine of ln of x, which will be contained within an e to the x function. So what we want to do is evaluate the derivative of sine of ln of x first. It's pretty clear cut which of these is the outer function. We have an ln of x trapped within a sine of x. So our outer function will be sine of x, and our inner function will be ln of x. Now we take the respective derivatives, which are cosine of x and 1 over x, and wherever it is that we see x in our f prime, we plug in our g. So it's going to be cosine of ln of x multiplied by the derivative of ln of x, which is simply 1 over x. So let's just go and plug in a x denominator right over there. That is the derivative of sine of ln of x. Now that we have that done, we can take the derivative of e to the sine of ln of x, where it is that we're going to treat this as the inner function. Sine of ln of x will be our inner function, and e to the x will be our outer function, because we have e being raised to the power of this entire mess. So we need the derivative of this entire mess as our g of x. So our f of x will be e to the x. Our g of x will be sine of ln of x. And our f prime of x, derivative of e to the x, does not change. It's e to the x. And our g prime of x is what we wrote out right over here, which is cosine of ln of x over x. So same procedure as before. Wherever we see x, we go and plug in our, wherever it is that we see x in our f prime, we plug in g. So this will be e to the sine of ln of x. All of that multiplied by the derivative of our g, which is cosine of ln of x divided by x. So this entire thing multiplied by cosine of ln of x, all this divided by x. And that is the derivative of our final function, of our initial function rather. And I think I've got one more example and I'm done, right? The derivative of cosecant squared of 5x. So essentially what we can do here is we can use that same subconscious chain rule application. However, I'm not going to do it for this one because it can get a little tricky because of this 5x. So essentially what we can view this as is cosecant of 5x. This entire expression will be squared. So this will be cosecant of 5x, all of that squared. So we want to take the derivative of cosecant of 5x first. So our outer function will be cosecant of x, and our inner function will be 5x. So cosecant of x, and 5x will be our inner function. And then we've got f prime of x, which is the derivative of cosecant of x, which is negative cosecant of x cotangent of x, multiplied by the derivative of 5x, which is just 5. So wherever it is that we see x in our f prime, we substitute in 5x. So this will be negative cosecant of 5x cotangent of 5x, all of this multiplied by g prime, which is 5. So I'm just going to pull that 5 out in front. So this will be negative 5 cosecant of whatever, cosecant of 5x cotangent of 5x. And then we can raise this entire thing to the second power by using an outer function of x squared. So we can use the chain rule once or twice, depending on how comfortable it is that you are using it. I'm using it twice for the sake of making sure that we do not get it wrong. So we have an inner function of cosecant of 5x, and an outer function of x squared, because this entire thing is being raised to the second power. So outer function, x squared. Our inner function will be cosecant of 5x. And now we just take each of their derivatives as we did before, 2x, and this mess over here is our g prime. So negative 5 cosecant of 5x times cotangent of 5x. So same as before, we plug in g wherever it is that we see x in our f prime. So we got 2 multiplied by cosecant of 5x. Cosecant of 5x. All of this multiplied by this whole mess. So we can tack on the negative right over here, multiply this by 5 cosecant of 5x cotangent of 5x, right? And now we can start joining coefficients. These will join together to make negative 10. Negative 10 cosecant of 5x cosecant of 5x cotangent of 5x. Now once again we have two more terms that can be joined together. Cosecant of 5x times cosecant of 5x is exactly the same. Sorry, I just got cut off there for a second. Now we can join these last two terms right over here, which are cosecant of 5x and cosecant of 5x. Those can be multiplied out and joined together to make cosecant squared of 5x, because essentially it's the same term twice, so we can just square the entire thing. So our final answer will be 10 cosecant squared of 5x multiplied by cotangent of 5x. That is a derivative of our entire function using the chain rule. Now let me check to see if I did that right. Yep, that looks about right. And that's pretty much all I've got to say on the subject of the chain rule. If you have any questions, go ahead and ask in the comment section below. I will make sure to answer them as quickly as possible. If you haven't already familiarized yourself with the long list of derivatives that I had provided on my website, go ahead and check that out. All of these questions and answers will also be available on the website as a separate PDF document. It's called Chain Rule Derivative, something along the lines of that. Just check out the free content page, and all of these examples and step-by-step instructions will be available in order to master the chain rule. So with all of that being said, I will see you guys in the next video, which will be... I have absolutely no idea what the next video is going to be. I actually have no idea. Anyway, I'll see you guys in the next video.